So if I had a chlorine, maybe I can just copy this here, edit it a little bit. Yes, that worked. So we've got now a chlorine atom here. And this chlorine atom, well, it's still not happy because it's got a gap. It's not got a full outer shell. If I get another chlorine atom, do I need to label that? Yeah, I will label that. Okay, but I'm going to demonstrate that this is the electrons are from different chlorine atoms. I'm going to do crosses again. I think maybe it makes more sense to put leave the gap on the right hand side this time. So essentially what happens is they share electrons. So how do we demonstrate that? We draw the circles intersecting, and then we kind of generally put the dot and the cross here. Oh, okay, fine. Oh god. Okay. Oh, right. This is ridiculous. There we go. So you put them in the middle. Now, if you want to think about what does this really mean, this idea of sharing the electrons? Well, imagine the electrons are kind of, these two electrons anyway, these two electrons are kind of orbiting the entire molecule. Okay, so this is now not a chlorine atom, is it? This is a chlorine molecule. Okay, and so a molecule, what's a molecule? Well, it is essentially a closed group of atoms bonded together that is kind of complete, done. If I got another chlorine atom, it doesn't join the molecule the way it does with lattice, with a lattice, with how ions join lattices, but it's complete, it's done. So this is how we form a chlorine molecule. So what about forming different different molecules? Well, the idea is that we always have to have a full outer shell. Now, you'll notice that I've got other ways of drawing molecules using these sticks here. Each stick, each little line, is essentially like a shared pair of electrons. Okay, so that's what you can imagine the sticks meaning. So I could draw these two molecules. It will take me a lot longer to do, but I could draw these using these intersecting circles if I wanted to, like the way that so H2O. So let's draw a water molecule. Hang on a second. Okay, so if I drew a water molecule, yeah, I'll do the. Now we've got 3 atoms. We're going to have 3 atoms here, but the hydrogens don't stay together, so I can give them the same, just a dot maybe. And then the oxygen's in group 6, so it's got 6 electrons in the outer shell. So it will have 2 gaps. So if I put 1, 2, 3, 4, and then I'm just going to put 5th one there. Oh no, I need crosses, didn't I? Like that, and the reason for that is because I can then take this, turn it around, put it there. Now I should be moving them into the inside bit there, but just to speed things up, like that. So that's our water molecule, which could also just be drawn like this. If I took 2 oxygen atoms, then they would bond twice. So you'll come across this kind of drawings a lot more in organic chemistry, but you can imagine each gap being like in these diagrams like little arms, and they all these molecules want to hold hands. So if I so carbon, for example, is in group 4, so it's got a gap, and that it's got a gap for 4 more electrons, so therefore it's got 4 arms. And if a hydrogen came along with 1 arm, then it comes along and joins that. Yeah, like that. So try to make that one line like that, and then all the other hydrogens join on as well. And now I know that it's not CH3. No, it's CH4, because everybody needs to make sure they're holding hands. So so this is what we mean by sharing. They kind of orbit the entire molecule. Okay, so that's covalent molecules. Now there is one other thing. I'd mentioned lattice in ionic lattices. You can actually have a giant covalent lattice, and an example of that would be diamond or graphite. If we think about what is a lattice, it's this idea of where it's not really complete. It could always carry on. So, and some people might say that a diamond is like a giant molecule, which is half right, kind of right, apart from the fact that molecules are complete, as it were. So, if I'm drawing this is not how this is a methane molecule actually looks, because we live in a 3-dimensional universe, and I'm drawing on a 2-dimensional plane here. So I'll try to demonstrate what it looks like. It's kind of got it's sitting on like a tripod, and then this one here is a bit like that, so it's kind of coming towards you. So yeah, it's called a tetrahedral, I think is the name of the thing. So this is how carbon's bonds would be arranged if they were all attached to different things. Now, if we had another carbon, then that would again form this other tetrahedral, and it could go on and on and on. And this is oops, that's got 5 bonds now. This is what a diamond, the structure of a diamond looks like, but I can't draw that, so I'm going to show you what diamond looks like. The diamond structure diagram, and there it is. No, don't want to save it. Copy. So there you go. So these are covalent bonds, which is why diamond is so strong, because it actually uses covalent bonds to hold the whole object together. And notice that the ones in the middle, actually I don't know that one has all 4 bonds taken up, but a lot of the ones on the outside don't, and so you could always add more carbon atoms to it. That's why we can call it a lattice. There are other types of lattices which I won't go into, but you can look at them yourself. Graphite, also silicon dioxide is strangely enough a lattice as well, covalent lattice. But we've got 7 minutes to look at metallic bonding. So I'm just going to get a diagram, and I can show you the key things rather than having to draw it myself. Remember what we said about what is it that makes a metal a metal? It has a small number of electrons in the outer shell. So when I have a bunch of metal atoms together, how do they bond? Essentially, a small number of electrons in the outer shell essentially roam freely, and we can refer to this as a sea of electrons. Okay, I'm just going to, because I haven't actually got anybody to write anything, and I'm going to be turning off editing anyway. I'm just going to put it on view now. It may look like you can still write for a moment, but you probably find that you won't be able to. So this is, we can refer to this as a sea of electrons. These electrons can float about all over the place, so they don't really mind which nucleus they sort of orbit, or which ion they orbit. So the other electrons, the ones in the shells underneath, are still fixed to that particular atom, but the ones in the small amounts that are in the outer shell are floating and freely moving amongst the metallic lattice. So yeah, so what kind of characteristics will this produce? Well, it's going to allow electricity to be conducted, because these electrons are able to move and they are charged. Therefore, we can call them charge carriers. They can carry their negative charge from one place to another. So if I applied if I had a positive plate over here, the electrons drift towards it, and I had a negative plate over here, they would drift away from it. So we have a current moving that direction. Not that direction, the electron flow would be moving that direction, the current would be going the opposite direction. So that's one of the characteristics a metal would have. Another characteristic would be that it conducts heat for the same reason, really. Only the difference between electric current, and heat conduction is that heat conduction, the electrons move randomly, but just by probability, those with a lot more energy will drift out in the same sort of way that what's it called in chemistry? Diffusion. This is chemistry anyway. They conduct heat because they can carry the energy from one place to another more quickly than in a non-metal, where in a non-metal you just have to pass the vibrations from one atom to the next. So that's what makes they also are malleable, because this whole structure allows the whole structure to bend more easily. So that's essentially what malleable means. Comparing that, they're also shiny, but the explanation of why they're shiny is a bit complex. I won't explain that. So what else is there to cover? Let me pause the video, and could you just in the last couple of minutes, could you ask any questions you'd like to ask, and I'll see if there's anything I've not included that's important.